Okay, we're going to deal with functions as series. We learned in our last video that 1 over x can be approximated by using a partial sum from 0 to infinity of x to the n. Now, this all comes from the fact that a sub n equals a sub 1, r to the n minus 1. But the thing is, if we let a sub 1 equal 1, that goes away. If we start counting at 0 rather than at 1, we no longer need the minus 1 bit, and we just get n. But r is a ratio. If r is a ratio, it can be different things. Well, things that can be different things are variables. So let's put x in place of r. Having accomplished that, we can now say that to sum up all of the individual terms of a geometric series, we have the sum from 0 to infinity. X to the n equals 1 over 1 minus x, because the infinite sum is a sub 1 over 1 minus r. But we already said a sub 1 is 1, and r, since it's a changeable ratio value, let's just let it equal x. So now, using this fact, we can find a number of other adjustments. The first adjustment I want to talk about is, instead of having f of x equals 1 over 1 minus x, let's say we have something similar but not the same. G of x equals 4 over 3 minus 2x squared. If we have that, you say, well, it's similar. It's a fraction. It has a subtraction in the bottom, has a 4 up top. But the thing is, there's going to be quite a bit of adjustment needed to turn this into this, which means if we adjust this bit, we also have to adjust the series that can be used to approximate it. So here's what we're going to do. We're going to say, what do I need to do to make this adjustable? With that, I could do the following. I can say 4 over 3 minus 2x squared equals 1 over 1 minus. Now, we don't want to use x again because the x in this and the x in this can't possibly be the same. So let's just call it u for clarity's sake. At this point, we want to solve for u. So we're going to cross multiply. By cross multiplying, I come up with 4 minus 4u equals 3 minus 2x squared. Using that, I can finish solving for u. Say negative 4u equals negative 1 minus 2x squared. Then I'm going to divide everything by negative 4. And I get u equals 1/4 plus x squared over 2. That means instead of having 1 over 1 minus x, I could replace this with 1/4 plus x squared over 2. And if I simplify that down, that should exactly equal that right there. But that means if I adjust the x here, I need to adjust it over here. So I now have the summation from 0 to infinity of something to the n, and that something is 1/4 plus x squared over 2. This is now my new rule that fits specifically with this problem, this g of x. So what we're going to do at this point is we could graph g of x. If I do that, it looks something like the following. If I were to take the sixth partial sum, so I want the sum, but I want the sixth partial sum of this formula, that would be 1/4 plus x squared over 2 to the 0 plus 1/4 plus x squared over 2 to the, well, first, plus 1/4 plus x squared over 2 to the second, plus, and I would do the same thing to the third, the fourth, the fifth, the sixth. Now, since I'm out of turn, let's just find the fourth partial sum. If I were to find the fourth partial sum and graph it, so if this is y1 and this is y2, and I put them on the same graph, I end up with this situation where the purple, the plum color, and the lavender color are close over a certain area, but they are not necessarily exactly the same as you go farther away. So what we can say is for at least part of the graphs match pretty well. So as long as I stay between these areas, the graph looks pretty good for an estimate. Outside of that estimate, they don't do a good job. So in this case, the graphs converge and come together. If they're out beyond that, they fly apart from one another or diverge. Now, just to prove that to you, let's go ahead and grab calculator. And I have graphed those items on the calculator. And you will see that when I go to y equals, I have the g of x in the top component. I have my long equation that goes on and on and on and on forever here in the second y equals. And when I graph them, they are very close for a certain region. But once you get out beyond that region, they diverge from one another. So that's what we're doing here. Now, there is one other thing we need to accomplish in this particular case, and that is over what intervals, what boundaries do they converge for, and what do they diverge for? So what we do for this is we need to take, and we know that in the geometric form, the absolute value of r has to be less than 1. Well, we went ahead and solved all this, and we said r, or u in our case, is 1/4 x squared over 2. So what we're going to do is we're going to take 1/4 plus x squared over 2. The absolute value of that has to be less than 1. Anytime we have an absolute value, we're going to do a positive version, and it stays less than 1. But we have a negative version as well, so I have 1/4 plus x squared over 2 is greater than -1. From here, we can actually solve this out. Let's multiply everything by 4, so I get 2x squared is greater than -4. And I get, 1 plus that. Here I get 1 plus 2x squared is less than +4. Minus 1, minus 1, minus 1, minus 1. Divide by 2, divide by 2, divide by 2, divide by 2. X squared is greater than -5/2, and x squared is less than 3/2, and I square root both sides. Okay, now from there, we can say x has to be greater than some value. Well, the square root of -5/2. And x has to be less than the square root of 3/2. If I actually go and find x is less than the square root of 3/2, I say second, square root 3 divided by 2, I come up with 1.22. Now, over here, I have a small problem because that's going to be imaginary. So when we looked at our graph, we saw that it was clearly symmetric and balanced. So we would say the interval converges when x is less than 1.22, and we can safely say when it's greater than -1.22. So we have now used a series to approximate a function as long as we confine that function to a certain area. With that, that is a more specific use of function as series. So